All right, so we're going to finish off Chapter 4 on multiple regression. And first, we're going to start out by talking about individual points and their influence over the regression coefficients, because not all points are created equal, and some actually help to determine the coefficients more than others, so we need to make sure that they're valid observations. And then we'll talk about ways of improving the multiple regression model, creating variables, adding polynomial terms to have the model be a better fit to the data. All right, so let's start out by talking about individual points in a regression model. So previously in the context of simple linear regression, we talked about outliers, and we talked about the detrimental effect that outliers can have on the regression equation, because an outlier tends to drag the line towards it in order to minimize the squared error. So when we do have an outlier, it has the potential to be an influential observation. In other words, one that has a lot of control over what the specific values of the regression coefficients actually are. And influential points are important to identify because sometimes they have a lot of influence over the regression coefficients. And outliers are sometimes, not all the time, these influential points. So let's review just briefly what outliers are in a multiple regression context, and then talk about what makes a point influential. All right, so just in general, an outlier is a point whose position is unusual given the shape of the data cloud. It may be unusual in terms of just a single variable, or it may be unusual in a combination of variables. So what do I mean by this? Well, let's take a look at the green and the blue points here. These are outliers in terms of x2 here. Let's imagine this is a homework 2 score, this is homework 1 score. We would see that the green and the blue individual have unusually high values for homework 2. The blue and the red individuals right here are outliers in terms of homework 1 because they have very, very large values of homework 1 here. Now this purple point is interesting because this individual has a pretty typical value for homework 1, right at about 3, and homework 2, just a little bit above 2, but it's very unusual in the combination of values. So if we look at the shape of the data cloud right here, the point stream, this purple point is pretty far away from where the rest of the points really fill up the scatter plot. So we would call this purple point an outlier, even though it has fairly typical values for x1 and x2, but it's very unusual in the combination. So let's review what the effect that an outlier has on the regression equation. Typically, in the presence of an outlier indicates the violation of the normality assumption, meaning that we can't use the regression model, but we know that an outlier can sometimes really affect where that regression line actually is. So there is a command inside library reg class called Outlier Demo. And this works very similarly to core demo, which we had looked at before, which illustrated the effect of an outlier on a correlation. So what I'm going to do is I'm going to click and make a point stream that looks to be fairly well described by linear regression. And what's going to happen is that the demo shows you two lines. The black line is the regression line on all of the black points in the scatter plot, and the red line is the regression line with all of the points. So if we were to add in the red point to the scatter plot already having the black dots here, that red line is the regression line that would result. So, okay, an outlier is something that is unusual in its placement with respect to the shape of the point cloud. So I could put an outlier way out here. This is really well separated from the point cloud. It has a very large value of y and a large value of x compared to the other points. And let's just see what happens when I add this point to the scatter plots. So I add that and I see that there's actually very little change in the regression line. So this black line right here is the regression line on all of the black points. Adding in the red dot doesn't really change the regression line all that much. So in this case, while this point is definitely an outlier, it wasn't very influential. Adding it to the data set didn't change the regression line all that much. Let's end this simulation and actually run it again. And I'm going to try placing that point in a slightly different location. So that first location, I placed that point kind of where the regression line was going anyway. And we saw that it wasn't very influential. What happens if I place a point down here? Well, by placing that red point down here, I see that it's vastly changed where that least squares regression line is going. So the black line is the regression line on the black points. The red line is the regression line on all the points after I've added that red point to the scatter plot. And so we see, like with our discussion in simple linear regression, this outlier has dragged the regression line towards it because it wants to minimize the squared error. And that outlier would have had a huge error with respect to this black line. So in this case, this point right here, definitely an outlier, and it's also very influential. It really determined where that regression line was going. Well, let's look at one more illustration. Let me draw another stream of points. And I'm going to fill up most of the scatter plot in this case. So here I have a very tight ellipse that describes the shape of the point cloud here. And I'm going to place an outlier down here. So very well separated from the rest of the points. But what we'll see is that this outlier actually didn't change the regression line all that much either. Sure, it dragged the regression line a little bit towards it, but it didn't change the slope all that much. And remember, the slope's the key quantity. That's what ties x and y together. And so adding in this outlier here did not influence the slope all that much. Both of these lines are tilted at about the same amount. So what we're seeing is that the effect of an outlier isn't constant. Sometimes it really does change the slope of the regression equation, and sometimes it doesn't. So it has the same effect with r squared. We've talked about what it does to r squared in the past, so I'm going to skip this slide. And now talk about outliers in a multiple regression context. So with simple linear regression, it's really easy to see the effect of an outlier on the regression line. But in multiple regression, that's hard to do. If you have more than just two predictors, well, it's impossible to visualize four-dimensional, five-dimensional space to see what's going on with 4 or 5 predictors. And so we need another method to figure out, okay, well, is this outlier influential? And one thing that's particularly dangerous in a multiple regression context is that very often there's no visual way to detect outliers from standard plots like box plots and scatter plots. So it turns out when you have a lot of variables, outliers can be completely hidden in the box plots of each of the predictors or the y variable, or even making scatter plots looking at the relationship between two of the variables in your data set simultaneously. So this kind of harkens back to what we had talked about with this purple point. If we had just looked at box plots of homework 1 and homework 2 scores, this purple point would have looked pretty ordinary because it's not the biggest, it's not the smallest value of homework 1 or homework 2. So it wouldn't have stood out. It was able to stand out in the pairing of x1 and x2 in the scatter plot. But if I have a whole bunch of different variables, say 10 different predictors, well, I could still have pretty typical values for each one of those 10 predictors, pretty typical pairings for x1, x2, x1, x3, etc. But it might be really odd in terms of the combination of all 10 predictors. And there's no way to make a scatter plot to really kind of flesh that out. There's no way to visualize 10-dimensional space. So we need to come up with another way to identify outliers, points that are going to be potentially influential. So there's a few measures that we look at. The first two go hand in hand, and that is looking at the leverage and the deleted studentized residuals of the points. And another measure is called the Cook's distance. So let's start out with the leverage of an individual in the data set. So the leverage of a point is really just a measure of how unusual it is in terms of its x values. So ignoring anything about the y values, how unusual is it in terms of the predictor variables? And the way this is going to work is that the leverage is going to be calculated as essentially a distance from the center of the stream of points just for the x variables, calculated with respect to the shape of the predictor data cloud. Now, this will be clear in the next slide. But with just simple linear regression, if I had just one predictor variable, 1x, the leverage is really easy to visualize because it's basically, okay, well, how far away is this point away from the average? So in this case, my predictor variable x ranges between about -10 and 5. The average is right at about 0, so if an individual had an x of -6, I would say that individual has a large leverage because it's far away from the average value of x. Pretty easy to look at with a simple linear regression because there's only one x variable. We can just look at the histogram. Now imagine that I had two predictor variables, x1 and x2. And imagine I made a scatter plot relating the values of x1 and x2 together so I could see how they were related. Okay, so here's how we talk about leverage in this context. So we see that there's an obvious relationship between x1 and x2. It's well described by a pretty flattened ellipse here. The center of the predictor data cloud here, just the scatter plot of all the x's, is right at about here. And let's consider these two bolded points on the left and to the right. Well, both of these points are the same distance away from the center of this data cloud here, at least measured by a ruler, but the leverage is the distance calculated with respect to the shape of the data cloud. So we see that the point up here on the upper left is just barely outside the ellipse that pretty well describes the shape of the data cloud here, whereas this point really sticks out like a sore thumb. It's about twice as far away from the center as the edge of this ellipse, so I would actually say that this upper right point has a much higher leverage than this point on the upper left because its placement is a lot more unusual with respect to the shape of the predictor data cloud. And so that's the way that we're going to think about leverage. We're going to imagine a kind of an ellipse that describes the relationships between all of the predictor variables, the x variables, and we measure how far away the point is from the center of that data cloud with respect to its shape. So if we have more than two predictors, we're pretty much out of luck because it gets harder and harder to visualize 3, 4, 5-dimensional space. But this is essentially what's going to go on. The leverage is some quantity that's actually able to calculate that distance with respect to the shape of the predictor data cloud. Once again, using no information about y whatsoever. Okay, so in order for a point to really be influential, we have to have a high amount of leverage. Back in the demos that we just saw, if we placed a point kind of where the stream of points was going, we saw that it wasn't necessarily influential, but this point definitely has a large leverage. So in this case, this point does have a large leverage, but it doesn't happen to be influential. This point over here has a very large leverage because with one predictor, our x data cloud is just basically a histogram of the values from 0 up to 0.5. So 0.8 is very far away from the average. This has a high leverage, and it's also very influential. It's not really in the direction where the stream was going. And in our third example, we saw that, okay, if we draw a point cloud and then put an outlier that is pretty far away from that point cloud, this guy wasn't very influential at all. It doesn't change the slope all that much. So the issue with this guy is that you'll notice that it falls pretty much right in the center of the x data cloud. In this case, simple linear regression, there's only one x, so basically the possible values of x I get are from 0 to 1. This is placed right at around 0.5, so this point actually does not have much leverage, has a very low leverage. So even though it's really far away from the stream of point, it's not where that stream is going, this point here isn't very influential. So here's the key insight. In order to be influential, you have to have a high leverage. However, that's not enough because this guy over here had a high leverage but was not influential. And that's why we look at this second quantity called the deleted studentized residual. So from that previous slide, it seems clear that a point needs to have both a large leverage and be placed in a position where the regression line wasn't already going. And so a measure of how far away the point was with respect to where the regression was going is called the deleted studentized residual. And basically what the deleted studentized residual is if we were to draw a regression line without that individual point and then measured how far away that point was from that line, that's my deleted studentized residual. It's normalized to kind of give me an idea for how far away it is in terms of the variability in the point cloud. So this guy would have a really huge deleted studentized residual because with respect to how scattered these points are from the line, it's super far away from the line drawn without it. So basically in our demos here, we can visualize the deleted studentized residual because it's just the distance of the red point from the black line. the point or the residual of that point made from the regression line containing all the other data points in there. So in order to be influential, we have to have a confluence of two events. You have to have a large leverage, be very unusual in terms of the x values, and have a large deleted studentized residual, be really far away from where the regression line would have been going without that point. So here's the rule of thumb here. A point is considered influential if two things occur. It has a large leverage, it's unusual in terms of its x values, and a large leverage is defined to be 2 times k plus 1 over n, where k is the number of predictors and n is the number of observations. So it depends on the data set itself. A large deleted studentized residual is one whose value is bigger than 2 in magnitude, larger than 2 or smaller than minus 2. So two numbers we have to look at to determine whether or not a point is influential. Some guy named Cook a long time ago said, you know, two numbers, that's kind of a hassle. Let's just come up with one. So he tried to combine both of these measures, and he came up with a number called Cook's distance. And the larger a point's Cook's distance, the more influential that point is. However, there's no well agreed upon cutoff for exactly what makes a point influential, how large Cook's distance needs to be. So we're not going to talk too much about Cook's distance. We'll stick mostly to leverage and deleted studentized residuals. Okay, so how do we actually find these influential points? Well, what we're going to do is we're going to make a plot called the influence plot that shows us what the leverages and the deleted studentized residuals of every single point in our data set actually is. So here's an example of an influence plot. On the vertical axis is the deleted studentized residual. It's basically how far away those points would be from the line drawn to the data without that point. And on the horizontal axis is the leverage, basically how unusual that point is in terms of the X data cloud. So how far away is it from the rest of the stream of points with respect to the shape of the data. All right, and you'll notice that the size of the points varies. And the way that this works is that the size is proportional to the Cook's distance. So the bigger the point, the more influential, at least in terms of Cook's distance. Okay, so to be influential, we need both a large leverage, and this vertical line here separates small from large leverages, so to the right of this line, and a large studentized residual, deleted studentized residual, so bigger than positive 2 or lower than minus 2. So the influential points are going to live in the upper right and the lower right quadrant of this plot here. And in this case, this is the salary data set predicting salary from experience, education, and months. We don't see any influential points. There's no points up here, and there's no points down here. This big circle right here, the center, is actually just barely above this horizontal line, so its deleted studentized residual is something like minus 1.95. According to our criteria, we would say that, nope, not influential. So in this case, with the salary data set, it doesn't look like any particular individual has more influence over the regression coefficients than others. And so that's a good sign. All these points are more or less created equal. In R, when you run the influence plot command, it'll actually print out the row numbers of the influential points. If it doesn't find any, it'll come out by saying, hey, integer 0. There's nothing there to look at. All right, we've talked about the body fat data set, trying to predict someone's body fat percentage from physical measurements. And in this case, we see a single influential individual. So large leverage is to the right of this line. Large deleted studentized residual is above and below those two horizontal lines. And there's one individual right here. So what makes this individual influential? Well, it turns out that belongs to individual 39, the 39th row in the data. It turns out that's actually the heaviest individual. So that's maybe one reason why they had more control over the coefficients than others. They were just really well separated from the rest of the X data cloud. They had really unusual physical measurements, and it makes sense. The heaviest individual probably looks quite a bit different than the rest of the individuals. All right, we've also talked about the census data set, predicting the fraction of households that actually respond to the census forms. And here we see a lot of influential observations here. So here are all the row numbers of the influential points. And these are all the guys who have X's marked through those points here. So large leverage to the right of that vertical line, and large deleted studentized residual above and below those horizontal lines. All right, so after we've identified these influential points, what do we actually do with them? Well, number one, we want to print out those rows and verify that there aren't any issues or typos with those observations. Very often in business analytics, you'll be handed a data set that has a lot of issues. The data will have been inputted incorrectly or just some error might have happened. So you want to make sure that they're valid observations. And then you want to follow that up to determine if you can see what makes it unusual. So you'll want to print out the particular row of the data set that corresponds to that unusual observation. So if row 43 was flagged as influential, you'll print out row 43 and then look to see, well, what are its x and y values? Remember, you can get a summary of each predictor and each variable in the data set by doing summary on the name of your data frame, and that'll print out that 5-number summary, the minimum, maximum, median, etc. And you can just look to see, okay, well, is it obvious why this individual might be influential? Did it have the biggest Y value? Did it have the smallest X4 value, etc.? Now, think back to the previous discussion. Sometimes influential individuals, outliers, have very typical values of the predictors but are unusual in the pairings. So it might be the case that you don't spot anything unusual in this individual just by looking at the X and Y values. That indicates they must be unusual in some pairing of those observations. So, okay, once you've identified what makes the individual influential, what do you really do with it? Well, not much. So unless it's really a typo, you're not going to delete that person from the data set. It's a genuine observation. And so if you really wanted to see how influential they really were, you could always try fitting a separate regression and seeing how much those coefficients change. It's never a good idea to throw away individual points unless you really have legitimate reasons to do so. Otherwise, you're going to get a very misleading impression of how well your model fits the data. These influential individuals are ones that are kind of exceptions to the rule. Remember, regression is a simplified model of reality. We know reality really can't be well modeled by a regression. Regression is just trying to do the best job that it can. So, of course, there's going to be individuals that really aren't well fit by the model. The model's wrong a priori here. And these are just a way to figure out which of those individuals stick out like a sore thumb. All right, so I will end part 1 here.